Hello and welcome back to Calculus 1. This is the part 2 of the last section, chapter 4 on antiderivatives, also known as integrals. Last time we did a lot. Well, we'll still have to do some examples and review and properties. So last time what I said is that integration or antiderivatives are backwards derivatives. So if the derivative of x squared is 2 to the x, if the derivative of x squared is 2x, then the integral of 2x is x squared. And now we know that the constant gets destroyed by the derivative and cannot be reconstructed. So we just put plus c, because once we do the integral, we don't know if there was some constant there. So we're just going to use plus c. And then we talked about all of the formulas. Integral of 0 is just 0 plus c. Integral of a constant k, so integral of, let's say, 3 would be 3x. And then we had this formula which had the x to the n, which covered 3 different types of functions. We had polynomial function, we had the radical and rational functions. They're all covered with x to the n. Then we had our good old e to the x, and for e to the x, there we go, good old e to the x, but we said that most of the time for e to the x you will actually use e to the ax, because usually you have e to the 3x, e to the 5x, or e to the negative x, right, which in this case a would be minus 1. So since you have usually something like that, then you can just put these things in there. And then the integral of 1 over x, which would give us ln x. 6 trigonometric integrals. And one important thing for these 6 trigonometric integrals is to note that tangent and cosecant and so on are not basic integrals. Basic integrals are secant squared, secant tangent, and cosecant cotangent, because as you can see on the right hand side you have 6 basic trig functions. So that's one of the adjustments that you have to do. Now the other integrals you are going to learn all of them in Calc2, so you will know all of the integration, but right now these are just the basic ones. And arc tangent, inverse tangent formula, which was the 1 over 1 plus x squared. And again, generally that 1 is not a 1, it's some other value, in which case it's represented as a, and then that a would show up the way you see it in the formula. So now, to illustrate a couple of these examples real quick, we can take the integral of e to the negative x dx, and we would understand this as integral e to the negative 1 x dx, which means e to the negative x over negative 1 plus c, and then we make it, I can just put negative in front, right? So negative e to the negative x plus c. Yeah. I should have restarted. I knew it after the update. I can feel that it's going to crash, because it's not responsive. So equals to negative e to the negative x plus c. It's still slow. So let's take a look at these three properties which allow us to combine these functions. So number one, integral of f of x plus g of x dx is equal to integral of f of x dx plus integral of g of x dx. So technically this tells us that we can, if we have two different functions added together, let's say polynomial and whatever else, exponential, you will take integral of each one of them independently. We have the same thing for negative, for minus. So integral of f of x minus g of x dx would be integral of f of x dx minus the integral of g of x dx. And finally, if you have some kind of a constant multiplying the function inside, you can kick it out, just like we did with every other limit and derivative. So these are the three. You will have special formulas, again, for multiplication and division. There will be special formulas. So you don't worry about that till Calc 2. Right now, we only have either basic algebraic manipulations, or we'll have this stuff where you split the integrals. So now, where is this? Generally, you don't think about these rules too much because they become second nature from day one of integration. You know that if you have multiple functions for derivatives, you take each one independently as long as those are added or subtracted. If they're multiplied, you have to use product rule. If they're divided, you have to use quotient rule, and so on. Same thing here. So if you have the integral of, let's say, x squared plus 6x dx, first what you are going to notice is notation. I have x squared plus 6x in parentheses. And the reason for it is because it's supposed to be multiplied by dx. And we'll see that in 30 minutes why. So if you have multiple terms, you have to use parentheses, because all of those terms need to be multiplied by dx. Now, as you practice integration, you will be writing the solution immediately, because this is, right, both of these polynomials. But now, since we are practicing for the first time, you can write integral of x squared dx plus 6 integral x dx, just to show that these are in fact basic x to the n integrals with extra fluff around, right? So you have two of them, so there will be two separate integrals, and then you also have that 6 that you kick in front. So integral of x squared is x cubed over 3, plus we copy 6, and then integral of x is x squared over 2, and then we have plus c. We know the formula from last time. It was x to the n plus 1 divided by n plus 1. So that's what we get. And now we can just write this as 1/3 x cubed plus 3x squared plus c, and be done with it. Say integral of 9 over 16 plus x squared dx. Now, these are the ones that are tough to see if you don't practice, obviously. This is the inverse tangent one. It might not look like inverse tangent because you are used to 1 over 1 plus x squared. But I did tell you that this number over here could be a, anything else other than 1. And the number on top, basic knowledge of fractions is that that's the number that multiplies the whole fraction. So that one can be kicked outside. So 9 you can kick outside, and now this becomes 4 squared plus x squared, and it's in the form that we are expecting for inverse tangent, which is 9, and then you have 1 over a, which is a quarter, inverse tangent of x over 4 plus c, and then just 9 times a quarter is 9 quarters. So 9 quarters, inverse tangent, x over 4 plus c, and that gives us the answer. Any questions, concerns? So we peel that 9, kick it out because it's a constant. That's the rule number 3, right? Where a number multiplies the function and you kick it outside. So that's number 9. And then it becomes 1 over a squared plus x squared, or x squared plus a squared, whatever, doesn't matter. And that gives us inverse tangent. Now, what I like to do is immediately to flip this question and have it as 16 plus x squared divided by 9 dx. In which case, it's no longer inverse tangent. Same players, it's just the fraction is flipped. Well, this problem is just, right, basic. 1 over 9 you kick outside, and now in integration you have 16 plus x squared dx. And you know that when you have multiple terms, you integrate each one separately. So without writing all those unnecessary steps, we just have 1 over 9 times 16x